Hey, everybody. We're recording in case that influences your choice of things to say.
Uh,
And God help me, it hasn't influenced me at all. So do as
I
I
don't
say,
think
not as I do.
I don't think God could influence you.
Yeah, well, it's a figure of speech for me. Let's see, where am I going?
I'm gonna go wash my hands real quick though.
Okay.
How are you doing today?
Doing good. Doing good for some unnatural reason. Who knows? I'm quite cheerful today. So let's see if this class changes that.
I hope it makes it even better or remains the same.
Yeah. Good morning, Michael. Good morning, actually, afternoon. Good afternoon, Jarrett, Jacob, Rebecca. I heard before Thomas is washing his hands. Not going to ask what it is that caused him to want to do that, but that's his business. I think we can all agree that's his business.
My first guess is lunch.
Ah, yeah. Is anybody, okay, we're all CS people here, right? Uh, Does anybody else like have, I can't work if my hands are dirty?
Yes. That's
Right,
why I have a big bottle of hand sanitizer right next to my computer.
yeah, anything on my fingers at all, I just can't stand it. I have to clean my hands. So, Thomas, we're talking about your recent trip, the one you've just returned
Yeah,
from.
yeah, my dorm room's basically right next to where I'd go do that.
Yeah. So I was just mentioning that I can't function if my hands are dirty. And I was wondering if that was common to CS people because I mean this is what we do. This is without fingers, we're theoretical computer scientists. So okay.
I mean, to be fair, most of what we work with is just theory until we actually get it to work.
Yeah. Well, hey, so I promised you at the end of last class that I would write you a demo of pipes, and I did. I wrote it immediately after the end of my workday, and I'm very happy with it. I sent you the link. Can you pull it down, like clone it or download it and do it on your computer? Yeah, there are fewer people all the time. That makes me sad in class. That does make me sad. So before moving on to synchronization, I want to go over the code for the demo that I wrote. Yeah, it's got some nice touches. It's got some places where we could probably take some lessons. So I'm going to show you that source code. First, I want to discuss what the idea behind the program. And so let me just draw a picture. Son of a gun. Oh yeah, oh yeah. Um, that's too bad. I am doing a file backup, which I expected to take less than an hour, but apparently it's taking more than an hour. And that is the connection I'm using for the QuickTime player. Let me see if there's another way of doing it. Um, uh, maybe share screen via AirPlay. Yeah, that sounds good. A plugin is required. All right, install it. Failed to start because port 7100 is in use.
We also cannot see what you are sharing on your screen.
Yeah, well, the problem is I can't either. So
Oh, okay, then.
that's a problem. And all right, so that's a problem. Okay, well, I'm gonna make stick figures. Let me share the editor. There. Okay. So the idea here is you've got a parent program. That's this program. And it's going to create two pipes. So one pipe is called to child. And then the other pipe is called from child. The parent is going to write, see, what can I use? The parent is going to write to the right side, the writing side of to child. So that would be index 1. And that is going to flow from the pipe to another program. And the other pipe is going to be reserved for traffic coming from the child. So the parent will read from the read side of the pipe. And the child that I'm going to use is just a program called cat. Okay, so the idea is each of these pipes is unidirectional. And as the names indicate, I chose the names carefully. To child, the right side belongs to the parent, the read side belongs to cat. From child, the right side belongs to cat and the read side belongs to parent. Now, interestingly, cat has no knowledge that this is taking place. So after the fork, but before the exec, the child, forked by the parent, is going to move around and change the values that are in the open file table. So it's going to reconfigure its standard input and its standard output in such a way that when cat replaces the child using exec, this picture is going to hold. You got the idea? So whatever what cat's going to do is just echo back whatever it receives. So the parent is going to write a string, cat's going to get it and send the string back to the parent. So that's the idea. It's a loop, the loop back. So I wrote this using an actual, I even made a GUI because I enjoy it, writing curses. So I did it in curses. So let me start up this. Okay, so here it comes, /parent. Okay, now if I pause this by entering Control S, you'll see on the left-hand side, the parent just sent 38 and the parent has just received 37. So line 37 went through the pipe to cat, cat echoed it back through the from child pipe back to the parent. Whoops, Control Q. That's unfortunate. All right, Control C. Let me run that again. What's unfortunate is Visual Studio Code was intercepting my Control Q. Okay, so here's the program in operation. Any questions about what the program is and how it's intending to use pipes?
So parent transmits some character, and then the child is going to print that and then also transmit it?
No, 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 no. Uh, y- uh, what you
So they're
see
not
here,
so parents going to emit some data, send it through the pipe, and then you're going to cat that data, and then you send it through the other pipe, and then parent is going to get it again?
yes. So the parent is doing all of this output. You don't see anything being produced directly by the child. So it's the parent that is emitting, as you said, data to the child, cat, and cat is simply repeating back to its standard output the line that it received. Now, its standard output is connected to, unbeknownst to cat, it's connected to the parent via a second pipe. Does that help, Cephas?
And the only thing you're printing is the final out?
Yeah, the only thing I'm printing is what I generated, which is LINE colon with the line number. That's the data I'm sending.
Would there be complications if the child is actually submitting data also? Instead of it just being only the parent sending the data to the child, which sends it to cat and then back?
Well, cat can send anything it wants, and it would show up on the RX side. So no, there's no complication. Cat is not aware that it's connected to pipes. To demonstrate something like this on the command line, so here's the source, so I can say cat parent.cpp, and I'll pipe it to cat, and pipe it to cat, and pipe it to cat, and pipe that to more. There it is. Okay, so without the more at the end, that's all there is. Right? So the beauty, one of the great ideas, capital G, capital I, of Unix is that everything is a file. Nathan Myhrvold, formerly a senior executive at Microsoft, used to complain that that's a terrible idea, but Nathan is wrong. It's one of the great ideas of Unix is that everything is a file. So what that means in this example is that a pipe looked like a file to cat. In fact, the cat's completely unaware. It's unmodified, it's unchanged, and it's unaware that it's standard in, it's C in, and it's C out, so to speak, have been hijacked and are doing something else. Okay. All right, let's marvel at the beauty of the code. Okay, so this is going to teach both pipes and curses. So let's begin though with the pipe. So looking at main, here's two sets of pipes, to child and from child. Create the pipes and indicate an error if there was an error. Okay. Now, what you see here is I'm indicating the error by a throw. So I'm causing an exception. One of the nice things about using exceptions to handle errors is you can code pretty much like you can program like your code's going to succeed. Now here I am explicitly checking for an error. And that's a good thing. But for example, if initialize parent, let's see, yes, initialize parent could potentially fail, but if it fails, it'll cause an exception. So I don't have to actually check its return code. So that's kind of a nice thing about using exceptions. So here's the fork. So far up here, it's one process in. There's the fork, 2 processes out. The only way you know the difference is by interrogating the process ID returned by fork. If it's non-zero, you're the parent. So if it is 0, let's initialize the child. Okay, so let's go up to, well, actually, I should use this feature here more. That way I can just click. Here is a use of a C++ attribute. In general, I do not use these, but I thought since I'm writing code for you to consume, that I might use it. In fact, this is the maybe less than a handful of times in my career that I've used C++ attributes. So this attribute says that under normal circumstances, this function does not return. Why? Because it's supposed to launch exec and it won't be back. It's supposed to launch cat, sorry, and it won't be back. All right, now, attributes in C++ are hints to the compiler. This one says the function does not return, and maybe that will influence the code generated by the compiler, improving its efficiency to some degree. Is that useful here? Probably not, but I wanted, so I did include that attribute only in the interest of providing an example of an attribute. So once again, attributes are hints to the compiler, which may modify its behavior. Okay, I've got some asserts in there. And this will ensure that toChild and fromChild will not be null. If you pass a null, the program should crash. So good practice there. Okay, now we start moving around the pipes. So watch the, read the comments. The child wants the right side of the pipe of, right side of fromChild to be its standard out, right? So let's look at fromChild. It wants its the right side of fromChild to be its standard out. So dupe2 closes the pre-existing standard out, which was attached to the screen, and duplicates makes file descriptor number 1 to be equal to the file descriptor of the writing side of the pipe fromChild. Then it closes the writing side. Now you've got 2 copies. There are 2 right side that are open, the original and the one that's been duplicated into file descriptor number 1. So you've got to close the other one, right? The only one you want left open is the one that's in file descriptor number 1, standard out. If you leave right sides or read sides dangling, it produces unpredictable results. Okay, by the same token, the read side of toChild, you're the child, this is the child executing the code. So the read side of this wants to become standard in of the child. That's why you've got that there. And once it's been duplicated, close the unnecessary original. Now, the child is not going to be writing to child. It is the child. It's going to be reading from. So I'm closing the right side of to child because the child doesn't use it. I'm closing the read side of from child because it's not going to use it. You have to do these bookkeeping steps to make to prevent any unpredictable behavior. Okay, and then the exec. Now, if the exec fails, it throws an exception. Okay. Now, let's go look at initialize parent, and you're going to see there's reciprocal code matching every one of these. It's reciprocal in that the roles are reversed. The parent writes to child, and it will read from child. Okay. Now, there's something cool here, and that is I configured the read side of the from child pipe to be non-blocking. If ordinarily, without doing this, ordinarily, if you read from something, you'll block until there's something to read. But I wanted this program not to block so that it continuously updated its GUI. So I set using FCNTL file control. So I set the read side of from child to it. This is gets the flags that currently exist. Then I set the flags ORing in non-block. You see that? In normal programming, I use the binary OR. Any questions?
Can you explain why you did that again? Why you didn't want to block?
Well, take a look at the output of the program. And take a look at the output of the program. So every time you see something change on the right-hand side, that was a read. And if this parent program blocked on the read, then the output, the transmit side would stop running because the program was blocked. So this program will keep transmitting even if there's nothing available to read. Because when it goes to read, if there are no characters available, the read will fail in an identifiable way, and I'll show you that code next. So does that answer your question, Morgan?
Yes, thank you.
Right. You know, many times when you're writing code that has to interact with the real world, maybe it's a game. The main loop of the game can't block, because if the main loop blocked, then the game would stop until something happened to unblock it. So very, very often you'll find special code added to programs that interact with people and are supposed to continuously run that use non-blocking IO. Okay. Now, there's another way to do IO called asynchronous IO. That's a little different. So asynchronous IO would be, for example, when you write, but you don't wait for the write to finish. So if you're doing really high performance code and you want to write to a file, probably you want to put the writing portion into its own thread. But you might also choose to use asynchronous input output so that when you say write, that just launches the write, but the code returns immediately. And sometime later, the write completes. Now, asynchronous IO, if you've done any JavaScript, you're familiar with the idea because JavaScript is mostly asynchronous IO.
Okay, quick question on async. Doesn't async ultimately have to go on some different thread somewhere, somehow? Because like I don't see how you can do async on a single like physical processor. Because a single core has to process everything sequentially. That's how it works.
In fact, Cephas, you do not need to have another thread to do asynchronous IO. So let's say you have just the one core, just the one thread. You launch the IO, and the code that you're using is an asynchronous IO. It's a different function, or at least different flags set to the common function. And so you launch the IO, the function returns immediately, and then somehow there's a message of some kind sent to you to flag that the IO is completed. Now, a second thread is not necessary because the remainder of that IO operation is handled in the kernel. Okay?
Yeah, but it's not ultimately. I guess it's async, but everything still has to be computed sequentially. With like
Well,
the actual execute, like perhaps not IO specifically, but if I want an async function, I want something that does some work. Perhaps it just I don't know increments a variable a billion times or whatever, and I make that asynchronous. If I don't actually have a different thread or physical CPU core, the operating system is just going to switch and then do that and then switch back and then do that and then switch back. Perhaps to the program it looks async, but ultimately it's sequential because a single core can only process things as it goes. You seem to get what I'm saying?
Yes, I do. I do want to draw your attention to a distinction, however, in that I was talking about asynchronous input-output, which involves the kernel. And your example cites just computation done in the user program.
I believe if it's at the kernel level, the kernel is still running on the same core.
Okay. Well, you've been through the operating system course, so you know that the notion that you own the computer is a falsehood. It's a lie. It's a fraud, and courtesy of the operating system.
Well,
It's a good
yes,
fraud.
but the kernel itself is running, if you have a single core computer, is running on that same core.
Yeah.
The actual instruction set, the architecture, can only compute one thing after the next. It can only do one thing at a time. It can do a lot of things over a short period of time, but ultimately you have to give it one instruction, then the next, then the next, then the next. Even the operating system is running on the actual core, so it can only, everything can only ultimately be sequential. It's like the illusion of
Well, in the absence of threads,
in the absence of threads
and also in the absence of other processes.
but even the other processes, their asynchronity is an illusion. They just constantly switching back and the CPU is being told to do different things, but it's still sequential. I'm doing one process's works, and then the next, and then the next, and then I'm going back.
All right, well, anyway, but coming back to an important question, what's your point?
That's all I was asking. Because like I've heard about async stuff on a single physical core, and I just don't see how it can actually be async. Just like you're not actually running multiple programs at once or independently, the CPU is still going to sequentially go through
Mhm.
and update them.
Well, I'll grant that. Somebody's got to do it, right? But from the perspective of your program, you've launched the I/O and you're not waiting for it to complete. So somebody's going to complete it. Don't know how, don't know who. Let's just take for granted that it does get completed somehow. But in the meantime, while that I/O was taking place, your program was able to go on and execute different code rather than waiting for the outcome of the I/O.
Okay.
Okay. All right. So let's take a look at the main loop. Using string streams to allow me to use easy formatting. So I use a string stream to easily format line, colon, and a message counter. Turn that into an ordinary string. And then I'm using the low level of write to a file descriptor. So I'm writing to the writing side of to child. That's going to send it to the child. This low level write requires use of a C string. So I turned the C++ string into a C string using its method, C_str, and you also need to tell it how many bytes to write. So this is continuously writing new lines to the right side of to child. If it gets something from the child, it'll add it to the window. But this is non-blocking. So if there's a full line, if a full line isn't available, getLine returns immediately. Okay? And then we're going to sleep for a quarter of a second, just so that it doesn't go too quickly for us to watch.
I guess I'm still having a little bit of confusion with the string stream. What is that like, and how is that different from, say, a normal string?
Well, let me explain it this way. You know what CIN is, and you know what cout is in particular, more importantly, cout. So cout, you can use that for formatting your output, right? And cout generally is, as far as you know, is connected to some output device, usually your terminal, correct? Okay, so a string stream is just a memory buffer where you can do the same type of formatting operations, and it just gets accumulated in memory, and then you can read back the entire result. So it's exactly like cout, only there's no device. It's just a memory buffer. Got it? Good. Very handy. Before string stream, this was a real pain in the ass in C. Okay, any other questions? So you're welcome to look at this code You can look at this code and see how to program curses. For example, here in its screen to start up curses, create two sub windows that are side by side, enable them to scroll vertically. This causes refreshes to take place. It also draws the nice border. So this draws a nice border around the window. This adds the letters TX on top of the border at the top, and this one on the bottom. But this class isn't about using curses, so you're welcome to review that on your own time. I would like to turn to this function, however. Where did it go? Get line. Okay, I want to make the text a little smaller again. No, I'm actually running the wrong. There. Okay, so now you can see the whole function. So getLine I thought was kind of cool in this implementation, but I want to point out, I'll tell you what I thought was cool. This is kind of elegant because the caller doesn't need to manage the string itself. Everything is self-contained here. And to do that, the context is after I've sent a whole line, I've gotten a whole line. After I've done that, I want to memset essentially the buffer over again. You're familiar with why you'd need to do that. I need to clear out the previous line before I start working on the next line. So I'm using a C++ string, so I'll just use erase. I don't need to use memset. But I'm keeping track using a static variable. I'm keeping track whether or not I need to do an erase internal to this function, so that the caller of this function is ignorant. Whenever it gets a string, it uses it. It doesn't worry about managing that string. Okay, now it occurs to me though that using a static variable, first of all, have you used static variables and do you need a refresher? Would you like a refresher on what it means?
I'm interested in having that refresher.
It will be my pleasure. The word static in C++ and C actually has many different meanings based upon the context in which they're used. For example, if you were to say static private to this file, we got to give it a type, of course, int. Okay, so that creates a global variable called private to this file, but no other compilation unit can see it. So for example, if you tried to make use of private to this file in an assembly language file, and you said, so .global private to this file, it will fail because it is marked as static at the global level. So what static at the global level means it's a global only in this file and no other file can see it. Thomas, are you pleased about that, or is there something funny that I'm not aware of?
Just something that you're not aware of within reality that I thought of.
All right. Is it pertinent to class?
Absolutely not.
Oh, okay. Then never mind. I thought maybe my teaching, what I'm having to say was pleasing to you, in which case I'd want to know about it, and I will never do it again. Okay, so, all right, so that's one use of the word static. Here is another use of the word static. When you use it inside a function relative to a local variable. it makes the local variable, instead of transient, it makes it permanent. So whatever value I leave this variable with when I exit the function, it will still have that value the next time the function is called. That's different from other local variables who get fresh copies every time. So Rebecca, is that clear?
Yeah, that helped out.
Good. Anybody else? Anybody else? Let me, hello, how do I make this? Okay, so, uh, Michael, is that clear for you? You may not have seen static before. Good, good. Jacob, Jarrett, Jordan? Okay, so what our computer science program at Carthage needs most of all is more students with whose name begin with J.
I'll be on the
Okay.
lookout and help recruit.
Okay, good, good. All right. So, but it occurs to me that there's actually a problem with this that is, I wonder if you might want to think about, because we're about to head into the part of the course where we start programming and using threads.
Wait, where we start using them?
Yeah, hardcore.
Oh God.
Okay. So the problem is, once we start using threads, use of a static variable, local variable, is going to be a real big problem, because there's no way to predict how many threads will be calling getLine at any given time. But this says there's only one needs a reset variable. There's only one. So if this was a multi-threaded program, that would be a bug.
How would
this-
that be a bug?
So this code functions correctly because it's not multi-threaded. If it were multi-threaded, the different threads were calling getLine, they'd each be calling getLine with a different buffer, and with a possibly different buffer, and possibly at different times. And the resource needs a reset. That variable is a resource, and it's being, if it's multi-threaded, you'd be sharing that resource amongst the threads, and that could result in incorrect execution. So the first hint that I'm going to give, the first pearl of wisdom I'm going to give about the correct use of multi-threading, is that any resource which is shared has to be protected in some way, or find a way to write the equivalent code without sharing resources. We'll study that much more soon. In fact, hopefully by the end of this class, because I'm pretty much done here. The only other interesting thing here is how to tell the difference between a read that failed and a read that failed because no characters were available right now. Remember, this is a non-blocking read. So the return value of a read, if it worked correctly, will be the same as the number of characters you asked it to read. So I'm asking it to read one character. If read returns a 1, that means it read a character was available, and I'm going to put it on the back of my string buffer. If it was a new line, I will tell the caller that I have a full line available, and I'll make sure that the next time I get called, I'll zero out the string. But what if read returns something other than a 1? If it's less than 0, it's an error. But it could be less than 0, signifying an error, but it's not really an error. It just says there are no characters available. So if the externally defined integer erno equals e again, that means there were no characters available. And it's not really an error, it just means there are no characters available now. Okay? So that's how you distinguish between a good read and a bad read, and between a bad read and an error. Or I should say, the difference between an error and there were simply no characters available. So if there are no characters available on a non-blocking read, the read will return less than 0, and erno will be set to E again. Okay? Okay, so have fun with this. I hope you study it and truly figure out what it does and what it means. Okay, time to ask for questions, and then we're going to start deeper diving into threads. So questions. Anybody?
I don't have any at the moment. Don't know what to ask.
Okay. Did everybody grab the code? Okay.
The code's in the message you sent out, right?
Yes, it is a link to the GitHub. So feel free to clone the GitHub or fork it or whatever. I wonder what I changed. Oh yeah, I added the static thing. Let me just get rid of that. Okay. All right. So I'm going to, let me get rid of that. And get rid of this. Let me open a new directory. Okay, so you do it here. A new folder called, it doesn't matter, T1. All right, let's write a new program. To use threads, you need to have thread. I want this program to sleep a little bit, so I'm going to need chrono. I need a vector, so I need that. And that's a pretty good start. Okay, so num threads equal, oh, what the hell? Let's do 50 threads. Why not? Let me save this so we get some squiggles. T1.cpp. Okay. And I have figured out, by the way, for people on the Mac, how to get rid of how to activate the IntelliSense properly. It's not easy. Let me see if I'll spend just a minute trying to figure out Wait, did it go away? Okay, fine, it went away. Good. All right. For in I equals 0, I is less than num threads, I plus plus. Let's do vector of thread star. Threads, threads dot pushback, and then new thread, and I need something to execute. How about void worker int thread ID? And all this is going to do is see out. Wait a minute. What do I want this to do? Oh yeah. So while true, that's true in a different language. So while true, see out hello from thread number PID endl, and now we want to sleep for a little bit. So thread, no, this thread, colon, sleep for, and now we give it a time. So how about we sleep for a 1/10 of a second? So that would be chrono, colon, milliseconds, and that would be 100 milliseconds is a 1/10 of a second. All right. So there's my worker. All it's going to do is print a lot. You know what? For now, I'll even make it a shorter sleep. So for 10 milliseconds, that's 100th of a second. So here's how you create the thread. You just call worker and give it an argument, namely I. All right, I hope that squiggle goes away soon. And then for this program, I'm just going to have it sleep for a little. This thread, sleep for, and chrono.
I don't think that squiggle's going to go away.
That, I don't know. We'll find out. We'll find out soon. Chrono, colon, I bet it's a Macism. Seconds, and I'm just going to have it sleep for 1
What's
second.
a Macism?
Yeah. What is a Macism? Yep. All right, so let's see. What does it say? No instance of the constructor. Void for int. Let me get rid of your faces so I can read the whole error message. Void int TID push back. Did I miss something?
Maybe you have to dereference or use the address, because I think of the worker process.
Let's try. Let's see if the compiler agrees. You see, there's a Macism. There's no error there. That is simply IntelliSense getting confused. Okay, well, anyway, let's see what happens here, huh? So /a.out. Okay, so I had 50 threads that ran in a loop 100 times per second. Each thread printed out their thread ID. What do you think? You like it? You see any problems?
It's too fast.
too fast? Is that the problem?
No.
Some of those IDs look wrong. Thread number 4618.
Output seems jumbled, at least a little bit, because there's 27 and then there's 31 and then there's 2.
Well, that kind of jumbling, being out of order, that's to be expected. Because all of the threads are operating independently. So who knows what order they're going to print in? That's not the problem I'm looking for to highlight.
Why are their numbers so crazy?
Well, coming out of order, that's okay.
But why
it's
are their
not just-
actual thread IDs so crazy?
Well, it's not the actual thread ID that's crazy. It's that all the lines themselves are crazy. Because one thread started writing this, but then another thread stepped in and started writing that, and then another thread stepped over that one. They're all using a shared resource. Remember I talked about that just a couple of minutes ago? What is the shared resource that's being used in this case?
See out.
See out, exactly. So what you're seeing is some thread started typing, started outputting, and then was descheduled. It was removed from the CPU so that another thread could run. Operating systems generally make a new scheduling decision after at most 10 milliseconds of running time per thread. So if you are compute bound, for example, you are calculating the last digit of pi, that's compute bound. Every 10 milliseconds, you will be removed from the CPU. You will be descheduled, or another word, preempted by the operating system so that somebody else gets a chance at the CPU.
Dad said it's my turn on the command line.
Okay, I don't understand what you meant, but it sounds good. Your turn on the command line? I don't get it. No explanation?
It's just, okay, you know how occasionally kids would just argue of parent X said it's my turn on the game or on whatever. I'm basically joking of you've been there for 10 milliseconds and someone else says, get off, it's my turn.
Right. Yep, it is like that.
And it's also like that when you have a sibling who wants to do something as well.
Okay. Yep. All right, so what can we do about that? We've got a shared resource that we want to protect. So in this case, what we want is at most one thread at any given time to be using cout. And if a thread begins using cout, we want it to finish. So there's this idea of a critical section. Critical section is a section of code that you want to ensure only a fixed number of threads can be in that section of code at any given time, typically one. You want, if I'm in that section of code, then I want to ensure no one else can get into that section of code while I'm in it. I want mutually exclusive access to a section of code. Okay, so we want to synchronize the activity of the various threads. So let's introduce something called a mutex. Can you imagine, think of what mutex stands for?
Mutant Texans.
Mutant text lines
Mutually
or
exclusive.
The answer to the question are words that I've used very recently.
Mutual exclusion.
Correct. Right. Mutex stands for mutual exclusion. Okay. So we're going to create a mutex at the global level so that all threads will share the same mutex. Okay. So mutex lock. Let's just M. Okay. So this has created an unlocked mutex. So before we access cout, we'll call m dot lock. And then immediately after using cout, we'll do m dot unlock. That makes the critical section this one line of code. Okay, so let's try that out. And now run. So what do you observe now? Compared
That
to here.
everything is
Wow, that's a lot.
working properly-ish.
Right, we have no control over which thread runs when. So the numbers are, it's correct that the numbers are out of order. But notice that there's no line that's stepping over another line. Okay? So what to review, what I've done is I've created a critical section which is being protected by a mutex. I lock the mutex before entering the critical section, and then I unlock the mutex as soon as I'm done with the critical section. Okay? Now, what would happen if, oh, I don't know, let's try putting the locks in other places. What if we just surrounded the entire while loop? Hey, what the hell? Let's try this. Okay, tell me, what's your guess? What's this going to produce? What output?
Is it only going to go once? Because the thread is basically only in the while loop once, and then it's like I exit because it's like I go it once and then it's unlocked, and like I don't see where it know what to do.
Okay, well, you're kind of in the right direction. Somebody help?
Only the first thread will get to run because it's going to lock it immediately.
That is almost exactly right. So you said only the first thread will get to run. That is, the second half of your sentence is absolutely correct, but where I would push back a little bit is, what does first thread mean?
The first thread to get to that function.
Perfect. Let's run. Let's run and see what happens. Okay. Nothing happened.
All you did was compile.
Oh. Thank you. So the first thread to get there got the lock and then sat on it. Now it happens to be thread 0, but there's no guarantee that it's thread 0 is going to be the first one there.
Would you like to test that theory?
Well, I can tell you that it is. Yep, see there. There you go. Yes, when you launch a number of threads, you have no idea which one will run first. In fact, you have no idea. So suppose you have a program which creates one thread. That program cannot predict if it will continue running or the baby thread, the brand new thread, will continue running immediately. So when you launch threads, you actually have no idea which thread's going to run next. So here was a 0, and I'm saying it just happens to be 0 the way that things are. We did see it run with a 1 once. It happens to be 0, but that's coincidence. Right? Okay. So that's no good. What if we put that there? So we have a lock inside the loop, but the unlock is outside the loop. Let's try that.
Wouldn't it crash because we're calling lock while it's still locked?
Well, I don't know. Let's find out. Oops. Explain.
We never have a condition to get out of the while loop. So it will never unlock.
And exactly. So the first thread to get to that line 13, the first thread, we don't know which thread it is, happens to be 0 a lot, but that's the coincidence. So the first thread to get to line 13 grabs the lock and then holds on to it for the entire time that the program is running, which means that nobody else can run. Well, we saw that before. But in this case, the first thread to grab the lock is also blocking itself. So grabs the lock, does the output, sleeps, goes to get the lock again, but the lock is already held. So it's actually blocked itself. All right, so what if we try, oh, I don't know. Let's try some other combinations. What if this was here and the unlock was inside the loop? Let's see what that does. That really didn't help, did it? So can you explain this? Anybody come up with an explanation as to why this has failed so badly?
It unlocks, another thread gets to the lock. It unlocks, but it'll never get back to the first thing that unlocked it because it never has a chance to. Because the lock is outside of the while loop.
Right, so each thread is potentially unlocking the lock while somebody else is already in the critical section. right? So you're pulling the threads are constantly pulling the locks out from under the feet of the other threads. Okay, so there is an art to designing synchronization. The short answer is these are the guiding principles that you must remember. So turn on your the part of your brain that remembers things in case it's not already on. So here's the part you have to remember. Any resource that is shared by threads must be protected and must be protected for as short a time as you can. Because remember, a solution, the first solution that we came up with, the second solution we came up with, just surrounded the entire worker with a lock. And what we saw is that didn't end well. This, by the way, is called a BFL, or big fat lock. So this is a fat lock. A fat lock is a cheater's way or lazy way of doing synchronization by throwing away all the benefits of multi-threading and using the lock to force everything down to single threading. So that's a BFL, big fat lock. All right. Okay. So somebody, any collection of you, repeat. What have you learned? What have you learned so far? What lessons?
Mutual exclusivity clauses exist and should be utilized extensively.
Okay. What else? All right. One thing I haven't tried is, so we saw that this worked correctly. This is pretty good. What if we move the lock down after the sleep? Okay, so that didn't do what we want. No, you've got to design your synchronization just so. For it to work properly. Okay. In the in the OS course, there's going to be two places where your head will collide with a brick wall. The first place is in understanding that you have to manage your own memory. But the second place, which is a much bigger, higher, thicker, stronger wall, is in the subject of synchronization between multiple threads. This subject that we're previewing in this class is the single most problematic part of wrapping your head around the lessons in operating systems. And wrapping your head around multi-threading is one of the most important gifts that I can impart to you. As I mentioned, the future is multi-threaded. Students that are comfortable with multi-threading are at an advantage over those students who do not feel comfortable with multi-threading. Because in your entire education so far, we've been promising you that the computer behaves sequentially. And now that we have multiple execution units within the same address space, that promise is no longer true. The computer will seem to behave as
So we're
if,
just going to need to get used to sequence breaking.
yes. So your operating system scheduler is a physical manifestation of Murphy. Okay? And Murphy's law. So the operating system is kind of guaranteed to pull the CPU out from under you at the worst possible time. And the only way to prevent that is to become an expert on protecting your shared resources. Okay?
Although in this case, threads are not necessarily non-sequential, since there's no necessary correlation between the number of threads and the number of physical execution units on the hardware.
Okay,
Just like
you'll have to speak a little more before I can follow you.
if you look on like the Mac, there are currently thousands of threads running. They're
Right?
not all completely asynchronous in the sense you probably have like 8 cores, I don't know, 16, blah blah blah. So it could just be the OS doing its scheduling magic like it does, where it seems to be non-sequential but technically is.
There are no sequential guarantees. None. Unless the programmer has coded them.
Yes, but in the physical, as in physically, certain threads are being run on the same core. So
Yeah.
their work is being scheduled where the operating system is switching between them technically sequentially, because there aren't enough physical cores to account for how many ever threads you have.
Okay. But the problem is even more insidious, though, is if you're going to be yanked off the CPU, you don't know where or when you'd be yanked off the CPU.
Yes, you
Let's
don't.
do, right.
But it is technically sequential in that you have to be yanked off the CPU in some finite time interval. Like you can't, it's not like
You
a
can't-
completely different physical processor that could be doing something completely unrelated at the exact same time.
Actually, as it happens, they do, but I understand your statement. For example, when we look at pipelining, an individual core, a single execution unit might be executing 10, 16, 30 instructions at the same time, just at different stages of the instructions. Further, take a look at Intel, hyperthreading. It's one core with 2 execution units. But the real problem is, and I hope you're not hung up on this sequential thing. The real problem is that the programmer has no insight into when and where its program will be yanked off the CPU. The best you can do is to arrange for protection so that you're not yanked in such a way that will cause problems. Let's move on to a different example. This one's a famous example. So let's say long counter equals 0. And so for long I equals 0, I less than 1,000 million I plus plus. And I'm just going to do counter plus equals 1. That's all it's going to do. All right. And then let's print. No, we need to do this. Now we need a join. We need joins. We didn't need joins before because we were just going to exit. Threads dot. Okay. All right, and now I don't need this. So yes, I am moving on to a fundamentally different program, but it's on the same subject. So print. Print. What language am I using? See out. Total is counter and L. And now let's change this. All right, so if I've got 50 threads and they each increment counter, which is a shared resource, hint, hint, if they each increment counter 1,000,000 times, the correct answer is obviously 50 million, right?
No, because some of them might do things at the same time and interrupt each other.
All right, let's try it. That apparently is, I did not save my code. There, come on. Oh, damn it, I'm using the keyboard shortcuts for a Linux machine. And of course that doesn't work. 50 million, 50 million, 50 million, oh, whoa, 49 million. Well, I got a different answer there. That's strange. Anybody have any explanation? I mean, given the same input, aren't computers supposed to be deterministic?
One of them stepped on the feet of another one that was running and caused it to
Either
out.
every single one did one less counter addition, or one thread just didn't run at all, or didn't.
Okay.
Having data races. Like you don't. Things are trying to read, and well, yeah, write the data, and you don't know when they're trying to do that.
Ah, okay. Yeah, I've tricked it into being worse. Look at that. Different answer every time. Okay, that's bad. And you know what's worse? If I ran this a number of times, enough times, sometimes it'd be a correct answer. Okay, so please explain.
One of them gets caught up in one of them finishes counting, gets in the for loop, and then joins everything else while they're still trying to count.
Not exactly. Let me put that in there. And G, let's run it again. Okay. All right. So what do we know about the instructions that are actually being executed? Let's translate this to some of this to assembly language. Now it's going to use counter in memory. So let's say it's going to be something like LDR X0, the address of counter. So this is equivalent to ADR X0 of counter without the equal sign. Then add X0, X0 and 1. Add 1 to X0. and then a store of, whoops, I didn't do that right. I need another instruction. LDR into x1 of what's at x0, and then a store of, let me finish correcting this, add 1 to x1, and then store of x1 into what's located at x0. Okay, there's the code for that instruction. Okay, so let's look at thread 1. That's one of the threads. So it loads address of counter, and it retrieves the value of 102. Okay, this is what you want to have happen. Adds 1 to make 103, puts 103 back in counter, correct? Right? Yes? No? All right. Now, suppose that this thread is not running by itself. Suppose at this moment, you get descheduled, and thread 2 starts running. Here's thread 2. And going down is time. Time is advancing as I go down. All right, so this loads the address of counter, and it retrieves, what value does it retrieve? What value? What value does it get?
Does it do 102 again?
Yep. And it adds 1 to make 103, and it stores, puts 103 back in the counter. And guess what? Yank. And now thread 1 is running again. When it adds 1, what is it adding 1 to?
103. Maybe.
No. What value does it have in X1? It has the value 102 in X1. So it adds 1 and makes it 103 and puts 103 back in the counter in memory, which means that everything that this did was blown away. Do you see how you can be interrupted at the worst possible time? Thread number 1 was interrupted, yanked from the CPU after it had loaded the value of counter into an internal register, a CPU register. Then it gets yanked, another thread comes along, perhaps increments not just once. Remember, this is in a loop. Maybe this increments 1,000,000 times while it's in the loop. So at this point, the value, forget about 103, maybe the loop runs 1,000,000 times. So the value of counter is 1,103. But then what happens? Thread 1 comes back. When last we visited thread 1, it had a value of 102. It adds 1 to it, makes it 103, puts the 103 back in the counter in memory, wiping out The million. This problem, by the way, has a name. It's called the hidden update problem. And it's generally described using ATM machines in a bank. Right?
And you don't want to lose your money.
Right.
So if you actually have completely different cores trying to access the data, you could have one actually writing to the memory location while another is trying to write something else to the memory location.
Yes, that will be managed by the CPU circuitry, but yes, you're right. Okay, so what is the shared resource? The shared resource is counter. So to get this example working correctly, you could go about it two ways. One is protect counter. The other is to reformulate your algorithm so that the shared resource goes away. So if you have a shared resource, and every shared resource you have must be protected when you have multiple threads. Please take a picture of this screen, a screenshot. Okay, so the remaining time will be just questions. And
Barbecue tonight.
barbecue tonight, yeah. And you know what? It's looking pretty good, maybe, that next year's barbecues will be in person.
That's
know
so
what?
exciting.
And you know what else? We had a great deal of help from campus's fundraising department. And we've had some generous alumni. And we have gift funds to pay for pizza. All right.
We're gonna have a really big party the first barbecue.
Right. Yep. I'm really looking forward to seeing some of you.
I was about to say. I'm honored.
No, in reality, I'm looking forward to seeing all of you, except the seniors. I don't want to see you next year unless you're coming for a friendly visit.
Black tie optional.
Okay, so questions about projects, questions about today's lesson. Anybody? The moral of the story for today, the moral of the lesson is everything you've ever known about execution being sequential is no longer true. So you've got to, going forward, you have to free your mind from this false given that one thing happens at a time. And instead embrace that the unknown, embrace the unknown. You really can't predict what the next instruction to be executed will be relative to some shared resource when you have shared resources and multi-threading, and unless you code for it. Always like the referee in a boxing match says, defend yourselves at all times. The key to multi-threaded programming correct multi-threaded programming is very simple. The key is any shared resource must be protected.
I have a question that is
Yeah,
largely unrelated.
okay.
It's actually remarkably unrelated. So you know how there are two computers in here? I'm in the lab, by the way.
All right, yeah.
What's on the other one?
I can't tell you.
As in you're not allowed or you don't remember?
I can't tell you the answer to that either.
Why wouldn't you be able to tell me that?
Well, I
Yeah,
can't tell you that. No, the answer is, Cephas, I have no bloody idea what's on those computers. It's been so long. I haven't been in that building in over a year to do any meaningful work. So, in fact, you'll notice that the NAS drive near you, then, if you're near it, was turned off. So is it off now, by the way?
Yes.
Okay, it had multiple drives fail in everyone's absence. So the data that was on that is probably gone. What's on those two computers? I have no idea.
Well, I have no way to access the other one, so I don't know either.
Okay, so that's the answer to your question. All kidding aside, I have no idea.
Was it important?
Well, that's an irrelevant. The answer to that's irrelevant because it sounds like you destroyed it. Did you?
No, I didn't. I'm
Oh,
asking
okay.
you if I can.
Go ahead. But you already destroyed one computer. Why do you need to destroy two?
Because I installed Windows on one, but I still need Ubuntu.
Okay, you could always run Ubuntu as a guest on the first computer and therefore have one less computer to maintain.
Yeah, but I have limited storage on the other one, and I'm actually using most of it, and I don't have
What?
space to dual boot.
Well, go ahead, wipe out the second computer, but keep in mind that when we all come back to campus, we're going to have to claw those computers back from you, okay?
Over my dead body.
Um,
No,
if you
just-
wish. Okay.
One question I have going throughout this is, can you control when the computer will yank your code? Or is there a case where you can make it purposely yank your code at a certain point? Like you'd prefer they'd make it yank it at this point if they're going to yank it all?
The answer to both of your questions is yes. The answer to your second question is as simple as that. Let's see, did yield? Is that what it's called now? That could be the C++ way of doing it. But to yield means you are choosing to give up the CPU. So that's the answer to your question. Can you choose when to give up the CPU? The answer is yes, by executing a yield. And then the first question, which was a bit more aggressive, there are actually things that can be done to prevent the CPU from switching to other tasks. But generally, those instructions are not legal for user level programs to execute. So there do exist instructions or ways to prevent a CPU from switching to another task, but those ways are reserved for kernel code or other magical system code. Anybody's code can voluntarily temporarily give up the CPU using a yield. Okay, Rebecca, does that answer the question?
Yeah, thanks for scratching that itch. I was just wondering.
Yeah, yeah. There are lots of circumstances where you might voluntarily want to give up the CPU. So it's important that you know that the yield function exists. Let's see, man, sched yield. Yeah, that's what I figured. Yeah, okay. Well, then again, it's a Mac, not a Linux machine. Okay, any other questions? Because we are out of time, so I can handle one more question maybe. Okay, everybody, get your projects in. You are so fortunate that you have an instructor who's so warm-hearted and caring that you could hand in your work late. But there are some limits, so get those projects in. Make sure you email me. I have been receiving emails for people who have turned in their projects recently. In the recent past, I haven't gone and regraded yet, but it is coming a weekend, and that's when I generally do the grading. So thank you very much. This is an exciting part of the course, not just because it's almost the end, but because the kinds of problems that we're going to be considering are really hard to figure out. Okay, so the most fun kinds of bugs are multi-threading bugs. Those are the ones that you might hunt for years, unless you know what to do. Okay, so I'll see you tonight, maybe at the barbecue. I look forward to it.
And then at random, the solution suddenly fixes itself, as per usual.
Yeah. Okay, bye-bye.
See ya.